Given a rooted tree with n nodes, an edge list, and a list of queries. Each query gives 2 nodes u and v, assign each edge weight 1 or 2. For every query, count how many assignments on the path from u to v make the total cost odd. Return those counts in an answer array, modulo 10 to the 9th plus 7. Example 1, a single edge connects 1 and 2. Query 1 has no edges on the path, so the answer is 0. Query 2 uses 1 edge, weight 1 is odd, weight 2 is even. Only one assignment works, so the output is 0, 1. Example 2, 3 queries on a small tree. Path 1 to 4 has 2 edges, giving 2 odd assignments. Path 3 to 4 has 1 edge, giving 1. Path 2 to 5 has 3 edges, giving 4 valid assignments. The output array is 2, 1, 4. In the advanced scaling version of this problem, we are no longer looking for just a single maximum path. Instead, we are bombarded with an entire queue of up to 100,000 independent query pairs, each demanding the number of valid edge combinations between 2 arbitrary nodes. Manually crawling the tree to count the edges for every single query is far too slow. We need a way to look up path lengths instantly. To achieve true constant-time lookups, we can leverage tree geometry. By running a single initial pass from the root, we can measure and cache the exact distance from node 1 to every other node in the tree. If our 2 target query nodes sat on the exact same vertical branch, finding the path length would be trivial. It would simply be the absolute difference between their precalculated root depths. But in a real tree, our query nodes will often live on completely separate, divergent branches. If we track their upward paths back toward the root, those paths will eventually collide at a single focal point, their lowest common ancestor. This ancestor node acts as the mathematical turning point, bridging our 2 separate branches into one continuous path. This intersection gives us a flawless mathematical shortcut to find our edge count m. The distance from u to v is simply the depth of u, plus the depth of v, minus twice the depth of their lowest common ancestor. By subtracting that overlapping top segment, we calculate the exact number of edges bridging our query targets without ever traversing a single path manually. Every query walks 4 boxes from left to right. First, a query pair enters the input box. Next, the LCA box finds path length m from node depths. Binary lifting powers that LCA step, prerequisite topic, not taught here. Then the combinations box evaluates 2 to the m-1, mod 1,000,000,007. Finally, the output box stores the answer. We allocate a depth array and a jump table up, node, j. A depth-first search from the root records every depth and the direct parent row. We treat that DFS as a known building block and do not rebuild it here. Next we preprocess the full jump table in one pass. Binary lifting fills the larger jumps behind the scenes, another black box we assume you already know. Each query calls query_LCA to find where the 2 paths meet. Path length k is depth of u plus depth of v, minus twice the depth of the LCA, that removes the overlapping top segment cleanly. Half of all weight choices on k edges give an odd total. So the answer is 2 to the k-1. We compute that with fast modular exponentiation and return it for each query. Let n be the number of nodes and q the number of queries. Preprocessing builds the jump table in order n log n. Each query finds an LCA in order log n, then raises 2 to the k-1 with fast modular exponentiation. Total time is n log n plus q log n, space is order n log n for the up matrix. We keep a depth array with 1 slot per node. The jump table up stores 2 to the j ancestors for every node. The main function takes the edge list and all queries. First call depth first search from the root, we treat that step as already built. Then build the full jump table offline, that step is also omitted here. Start with an empty answer list. Loop over every query pair U and V. Ask the helper how many odd sum assignments work on that path. Append that count to the answer list. Return the full answer array. The helper handles one query from U to V. Find their lowest common ancestor with binary lifting, omitted here. Path length k is depth U plus depth V minus twice the depth of the LCA. If k is 0, there are no edges on the path. Return 0 immediately. Otherwise return 2 to the k minus 1, modulo mod.